geochronology.
Thank you. Some very interesting talks this morning and raised some important questions that I'm hoping I'll be able to address some of those issues. This is a summary diagram showing the evolution of life after the cryogenian glaciations, including the first appearances of Ediacaran biota, appearance of small shelly fossils, Gasquier's glaciation, and then the dominance of bilaterian life after the Precambrian Cambrian boundary. There's a more detailed illustrations of major faunal turnovers by Mao Yanju and his colleagues. And it also shows the major changes in the ocean geochemical cycles, which is reflected into the large Sharam positive carbon isotope excursion and also the basal Cambrian isotope excursion. To put my talk in better context, what I'm going to be talking about is about a 40 million year time period that starts from the Gasquier's glaciation here in Newfoundland, and then the first appearance of Ediacaran biota. And after that, the Sharam big excursion, and ending at the Ediacaran Cambrian boundary. And I'm hoping to show you some geochronology data, which some are published, some have not been published yet. These are important. Geochronology is important because obviously we need to know the timing of these events at high precision to be able to say something about possible links between them. So the method we use is uranium lead zircon ash bed geochronology by isotope dilution thermal ionization mass spectrometry, which means we collect ash beds from stratigraphic sections of interest. This particular one is the ash bed below the Gasquier's diamictites in Great Colonid Island, the picture in the background. So we separate zircons, we put them into microcapsules, we spike them with a mixed uranium and lead isotopic tracer, and then we totally dissolve them in hydrofluoric acid. And then we separate and purify uranium lead by chemical methods, by column chemistry. And then we load that uranium lead on rhenium filaments, mass spec filaments, and put them in a mass spectrometer and make our measurements. So it's a very long, laborious, time-consuming, and expensive kind of technique, but the reward is high precision. Precision that can basically improve an order of magnitude or better compared to laser ablation, ICP-MS, or ion probe techniques or microbeam techniques. So this is a really old technique, has been around for a long time, but it has gone through major improvements in the last 10 to 15 years. One of the most important ones were zircon pretreatment by chemical abrasion, which basically allows us to, first of all, we anneal zircons at very high temperature, and then we leach them in concentrated hydrofluoric acid. It allows us to basically mine out those radiation damaged part of the zircon that are responsible for lead loss and usually give us anomalously younger dates. And that was a major improvement that was developed by Jim Mattinson, University of California, Santa Barbara. Other developments we had in that time period was the production of the mixed uranium lead isotopic tracer under Earth Time Initiative, which is very well calibrated, has been distributed to over 20 different uranium lead labs internationally. So something to remember is that every time we measure a date, or every time we measure uranium lead, we come up with 3 dates. So one date is based on decay of uranium-238, another one is based on decay of uranium-235, and the third one is just a lead-lead date. And these 3 dates are not at the same level in terms of precision and accuracy. We have learned through time that the 206-238 date is the most precise and the most accurate for reasons that I don't have time to explain the whole thing in this session, but at the same time, it is highly sensitive to lead loss. So being able to take care of the lead loss was a major step in moving away from 7-6 dates, lead dates, Upper Concordia intercept dates, and just focus on 206-238 dates as a way, as a best chronometer for calibrating the geologic timescale. So that was a major improvement. And almost all of the work that we are doing in modern times for calibration, for time-series calibration, for high precision work is exclusively using 206-230, weighted mean 206-238 dates. Now, all of these improvements take many years to come by. So if you're looking at the literature, it's full of geochronologic data of different vintages. They came out at different times, they're different protocols, different quality, and it often gets confusing, especially for a non-specialist, when they want to combine all this data and trying to make correlations. So that's why we're going back to some of the older sections, and we're redoing some of the older published dates with the new techniques and new protocols, with the earth time spike and with chemical abrasion, to be able to validate those older data. Now, starting from the gas gears, that's the main southern Avalon section of the gas gears diamictites. Work on this was done by Paul Myro, Ed Landing, Sam Bowring, and myself, starting in the late 90s and early 2000s. And you probably have seen that abstract that's been referenced many, many times. This is a newer section from the Bonavista Peninsula. Judy Poo, who was an undergraduate at MIT, worked on this section with me in the lab and out in the field with Francis Macdonald, Andrea Mills, and the colleagues. And then the results were interesting, and it was really important to be able to pull them all together and publish in one paper, the paper that came out in 2016. These are the data. Basically, to the right are from the Bonavista Peninsula, to the left from the Avalon. And if you just consider the Avalon, the gas gears data, it permits a total duration of about 1.6 million years for the gas gears glaciation. But if you combine the two data sets and you assume that they were synchronous, there was no diachronity, it only permits 340 million years. So it has to be shorter than 340 million years. So that shows the gas gears glaciation was very short-lived and probably was not an global Earth glaciation. Now, additional data from higher up in the section, from the Druk Formation and also from the Mistaken Point Formation, shows basically this date, 570.94, is about the same level as the first occurrence of Ediacarans in the section, in the southern Avalon. And that one is from within the Mistaken Point Formation, within the Ediacaran ranges of Ediacarans. Now, that, as has been discussed before, there is a strong taphonomic control on fossil preservation in these sections. Just because they show up here doesn't mean that Ediacarans didn't exist before that or even before the gas gears glaciation. And because the gas gears was so short-lived, it is unlikely had any significant effect on evolution of life. So that was the main conclusion of our study. Now, moving up to the Sharam carbon isotope excursion, this is the section from the subsurface in Oman. If you look at those dates, one of them is from South China, it's from Dushanto, the other is from Namibia, and this one is from Oman. It's actually from the same section. So this date at the bottom has been calculated by extrapolating down section. These are not direct age constraints. So Sharam remains work in progress because we don't have any direct age constraints. At this time, that's the best constraint we have, and it shows basically that the excursion could probably, the duration was between 5 to 11 million years. So still waiting for better constraints. Okay. Now, moving to the Ediacaran Cambrian boundary in Namibia, our colleague from Dresden set it up very nicely with new data and fossil ranges, so I don't need to get to any kind of details. Those are the dates already shown from Grotzinger et al. 1995. From the upper Spitzkopf member. One is from below the Ediacaran Cambrian boundary, the other one, so there's the boundary is actually a sequence boundary, and the next date is from right above the boundary, and that's also the first occurrence of a TEPD. So these dates were based on, these are before the chemical aberration and before the Earth time, obviously, and they were based on multi-grain analysis of air abrated zircon. So that should be kept in mind. Now we went to the same samples, basically zircons left over from the same ash beds, and we reanalyzed them with the new protocols, with the new spike, and with the chemical aberration technique. So that's the date from below the boundary. It's 539.32 plus or minus 0.13 million years. You see there is one younger analysis. If you take that as the age of deposition, that would be even younger. That would be about 538.5 million years. So we're not sure at the moment. The other sample gave a range of dates. See, a lot of them are reworked zircon, detrital zircon. The youngest one was 538.4 million years. So we can actually confirm what our friend from Dresden showed, that the boundary is actually younger, and that is true. It's not a matter of interlaboratory bias or any issues with the techniques. Now, moving on to the new data from Northeast Yunnan province in China that Mao Yan pointed out in an earlier talk. I don't need to get into any details. The Xiaotan section appears to be the most complete with the best chemostratigraphic record, has been discussed in multiple talks in this symposium. And there are also two additional sections, the old Meishuchun section and also the Liaowen section. They kind of line up in the eastern Yunnan province. Here are, again, the carbon isotope record from the Xiaotan, which is one of the main sections that we are working on right now. These ranges of small shelly fossils are old, obviously. There's been new studies. It shows transitional fauna going all the way down to the boundary. And the boundary is very well established, both based on the small shelly fossils and the carbon isotope excursion, the basal Cambrian excursion. So we had two ash beds, both of them very near the basal Cambrian isotope excursion. These are the preliminary dates from those two. And ages range from 539.45 to 539.37. These are 2 sigma analytical errors in the order of 100 to 130,000 years. So again, they confirm that the Ediacaran Cambrian boundary is indeed young. There's good consistency between ages in China and in Namibia. So the conclusions, basically the last of the Neoproterozoic glaciations occurred a little before 580 MA and lasted probably less than 340,000 years. So it was not a big glaciation. It was probably very little impact on the evolution of life. The Ediacaran biota started to show up about 9.5 million years after the glaciation, but again, that may not be the beginning of Ediacarans. That's the beginning of the record. Sharam carbon isotope excursion is still work in progress. We've nothing new since the Bowring et al. 2007 work on that one. There might be unpublished data somewhere, but that I'm not aware of. But and then some of these old dates, obviously, they have to be reanalyzed. They cannot be reconciled with modern geochronology data. And the ones from Namibia obviously shows younger age constraints on the boundary. And the new geochronology from Yunnan tentatively puts the boundary between 540.7 to 539.6. So it necessitates a reevaluation of the age of the Ediacaran Cambrian boundary, for sure, consistent with other data that are coming out from other labs on various Ediacaran Cambrian boundary sections. Thank you.